of smart healthcare technology, opportunity and challenges. So today we have a expert with us, Dr. C. Periaswamy. So C. Periaswamy possesses over 15 years of experience in teaching and research at national level at National Institute of Technology. He is currently serving as an associate professor in the Department of Electronics and Communication Engineering at the NIT Calicut. His research primarily concentrates on a design and development of electronic biosensor and piezoelectric device utilizing low-cost material for various applications. Dr. Periaswamy's research group is dedicated to create a low-cost MEM sensor and biomarker tailored to meet the specific needs of India. He has an extensive publication record with more than 120 papers in international journal and conference proceedings. Additionally, he has successfully managed 4 research and development projects funded by various government agencies like BST, SERB, and BETI. He has been honored with the Young Faculty Research Fellowship from BETI and the Young Scientist Award from DST, both from the Government of India. So, thank you, sir, for joining with us. Now it is over to you, sir.
Thank you, sir. Thank you for your introduction, actually. First of all, I would like to thank Honorable Director, Immunity Jaipur, and Chief Investigator, Professor Lauberger, other Chief Investigator of Immunity Jaipur, and other co-chief investigator, and particularly I thank this course coordinator, Professor Amit, for giving me this great opportunity. And also I thank Chief Investigator, particularly Vinith Saula sir, for giving me this opportunity and also giving opportunity as a NIT Calicut as a coordinating institution, actually. Thank you so much, sir, for giving me this opportunity. So can I share my slide, sir?
Yes, sir, please.
Sir, my slide is already visible, or should I say now I have to share?
You need to share it. Currently, it is not.
Okay. So.
Yes, sir. Now it is visible.
Okay. Thank you. Sir, it is clear?
Yes,
okay, thank you. Thank you. Thank you. Thank you. So, good morning to all the participants. I hope that the last 6 section actually you have enjoyed actually. So, and also you have learned many things regarding that smart healthcare systems. Okay. So, today actually I am going to discuss actually design and the development of electronic devices for biosensor and bio-MEMS applications actually. Okay. So particularly here, whatever the work I am going to discuss actually, that work is done by our research group, particularly research scholar actually. Okay. So this is the outline of my presentation actually. So I am going to discuss actually what are the biosensor, what is the need for biosensor actually, different classification of biosensor, and then I will discuss actually our research contribution, design and the development of electron devices for biomedical application, particularly I am going to discuss actually design and the development of biosensor based on algane HEMT transistor for different applications. And also I will discuss actually design and the development of that particular semiconductor material, which is zinc oxide thin film MEMS sensor for biomedical applications actually. Okay. So as we know that in recent years worldwide that life expectancy is increasing, especially in the developed countries. However, that the case of diseases, including COVID, have been grown in the old member of the population, not only old member, even it is affected in the all category of humans actually. Okay. So therefore, particularly actually, not only that cancer, sorry, COVID actually, and also particularly that cancer is the heterogeneous diseases that can be expressed differently among individuals. In addition, that the treatment may have a differentiated approach according to the type of malignant nepotism. So this our aim is actually to develop biomarker actually which will detect low concentration reusable for different diseases actually. That is the our aims actually. So that biomarker or biosensor actually one can find in the different domain actually, including particularly medical application have the highest demand actually. One can find that biomarker in medical domain actually. So, and also that biosensor, one can find water quality measurement, horticulture, even wearable sensor and other manufacturing industry actually. We can or one can see there are n number of biosensor and the biomarker we are using for to measure or to study the different diseases actually. Okay. So worldwide, that demand of biomarker actually day by day it is increasing actually. Okay. So from this figure actually one can easily understand that the global market regarding that biosensor actually day by day it is increasing actually. Okay. So what is the motivation of our research, particularly that is reusable biosensor? That our motivation is actually there are n number of biomarker already have been developed and demonstration. That biomarker it may that based on either semiconductor or it may be chemical route biosensor already have been successfully developed and demonstrated. But however, there is existing lack of cheap, reliable technology to screen life-threatening diseases like cancer. Because as I already told actually that cancer is the one of the major diseases actually which is affected most of the humans. So we have to develop actually reusable biomarker actually which will detect diseases like not only cancer, tumor, kidney malfunctioning each actually. Okay. So we have to, because we have to find that the diseases at the early stage. That is the most important actually. Because to detect this all diseases actually including cancer or tumor or that kidney malfunctioning, we have traditional techniques actually. For example, actually, one can that detect or find that diseases by using traditional technique actually, including MRI scan, biopsy, or that digital reactive examination method. And this all are the traditional method actually. One can use it actually, but that limitation of this two method is actually, for example, MRI scan is the first of all it is costly and it is radiation actually. So it is very difficult to spend cost as well as it will affect the human body actually. Other technique actually, biopsy actually, biopsy also one type of technique to that diagnose the diseases, particularly cancer, but it has limitation actually. So for example, actually, whenever you want to diagnose diseases, that cancer diseases by using biopsy method actually, we have to collect the material from the or sample from the that affected person actually. if you will not take that appropriate sample from the that particular portion or area actually, that will give false result actually. So that is the disadvantage of biopsy technique actually. That digital reactive examination technique also, it has a lot of more number of that limitations actually. So best method is actually biomarker actually. So that is the best method for to detect early stage diseases actually, for any diseases actually, including cancer, as I already told you, cancer or any other tumor things actually. So this particular work actually, our because due to that limitation of conventional technique actually, including it is expensive, time consuming, and particularly it is laboratory bound, and it is not portable. That is the more important points actually, that whatever the conventional technique we are using for it to detect diseases actually, it is not portable. So recent years actually, that researchers actually, they are developing actually reusable biomarker or biosensor by using that recent technology actually, which will give low manufacturing cost, fast response time, and it is portable, easy of use, and also it will give better accuracy. That is the reason actually why most of the research actually recently they focus on to develop reusable, invasive, non-invasive technique actually, because conventional technique actually, that including MRI biopsy actually, it is invasive technique actually. If instead of using conventional technique for to detect diseases actually, if we use biomarker based on semiconductor devices actually, it is non-invasive technique actually. So that is the more important actually. Okay, so before going to discuss actually our that research actually, our research contribution actually, I just to recall actually that fundamental concept of that biosensor actually. So we all are aware actually what is sensor actually. So here that sensor, that particularly biosensor is actually, it is nothing actually. It is analytical devices consisting of biocomponent, bioreceptor, and transducer actually. So here that bioanalytical devices actually, as I already told actually, there is biocomponent actually, which will react with the bio sample and it will convert into the bio or physiochemical signal. Then by using transducer actually, one can convert into the measurable signal, including it that measurable signal, it may be electrical or optical or other measurable signals actually. So that is the advantage of biosensor or biomarker actually. So that type of biosensor actually, or that in that biosensor actually, or that based on that transducer actually. So there are n number of method or n number of transition technique is available actually. It that transducer method, it may be optical or fiber optic, or it may be electromechanical or piezoelectric working principle actually. Okay, and that bio component, or maybe either antibodies, it may be that is cell or enzyme or DNA. This all are the example of bio component which will react with the antigen and convert into the biochemical signal, and then that biochemical signal actually, it will convert into the measurable signal by using transducer actually. Okay, so this is the basic working principle of biosensor or biomarker actually. So recent past actually, as I already told actually, n number of biosensor based on semiconductor materials actually already developed and demonstrated actually. So that by using semiconductor transistors actually, so we are able to convert biochemical signal into measurable signals actually. So for example, as I already told actually, so this is the example of how that bio sensor or system that block it will look actually. So here, so from that bioresistor actually, it will convert into whatever the that disease sample which will expose on the this particular sensor, it will convert into the biochemical signal, and this transducer actually it will convert into the measurable signal, and that measurable signals actually one can even interface with the our mobile devices actually. That is the advantage of this biosensor actually. Here that analytics may be of we can take from the human bodies actually, like that that is sample maybe it may be saliva, or it may be urine or blood or even sweat actually. So this is the samples actually one can easily collect from the human body, and we can um, test the what type of diseases affected that particular person. Okay. This is the history of nano biosensor actually. So based on or due to that development of nanoscience and nanotechnology actually, that nano biomarker actually reached at nanoscale level actually. Okay. So and also due to that advantage of CMOS technology actually, one can find silicon-based biosensor or biomarker in the healthcare systems actually, because silicon or CMOS technology is the matured technology, and one can find silicon-based devices in the healthcare systems actually. But and however, even though we have already developed actually by using CMOS technology, not only bio marker or biosensor actually, we are able to develop chip. Okay, so one can use as a portable devices actually, but that limitation of that silicon based devices is actually compared to other devices actually, it has lot of disadvantages actually. So that is silicon devices actually, first of all actually, it is not biocompatible compared to the other devices actually. So that's why actually this particular research, our research is focusing on design and the development of reusable sensor based on other component material. Particularly our research is focused actually alkaline temp transistor for biosensing applications actually. So this particular slides actually, it is showing actually how one can use that either silicon based semiconductor devices or other semiconductor devices one can use as a biosensor actually. Here we have shown actually that a different working principle of biosensor actually, as I already told actually, that the biosensor, that working principle may be either optical or even it may be magnetic based or mechanical based actually, because that sometime that biosensor or biomarker actually, it is not mandatory, it should be the sensor or it may be actuator also. Okay, so that is the so that a sensor may, that biosensor, it may be sensor or actuator also. So whenever we will design biosensor or biomarker actually, these are the parameter actually which will decide the performance of the biosensor actually. So that main parameter is actually sensitivity, selectivity, and repeatability actually. So these are the more important parameter whenever if you are designing the biosensor actually. Okay. So most important is actually selectivity actually. So we have to design sensor which will detect particular diseases actually. So that is called actually selectivity. Even if we expose that diseases sample even small quantity, our sensor should be able to detect. So that is the more important parameters actually, sensitivity and selectivity. Because so whenever you will expose that human samples like that serum or saliva or blood sample which is contain number of proteins actually. So we want to detect particular protein or particular that tissues actually. So selectivity is the more important parameters actually. Okay. So that motivation of or self motivation of design and development of temp sensor for different application is actually, as I already told actually, that the silicon based sensor has limitations actually, particularly it is not biocompatible. For example, suppose when you will expose, for example, if you are using that silicon based sensor for pH detection actually, so whenever you will expose or acidic or base samples actually, that base samples actually instead of reacting with that silicon surface actually, it will etching will take place actually. So that is the reason actually that the silicon based biomarker is actually, for example, it is not suitable for pH detector actually. Okay. So which is that pH is the more important actually parameter actually which will decide the young number of diseases actually. Okay. Because pH is variation in the our blood sample actually which will indicate the diseases actually. So to detect pH level in our blood sample or saliva or serum actually, it is more important actually, which will decide the diseases level actually. Okay, so that's why actually we have for our research is focusing on non-invasive high electron mobility transistor based devices for different biosensing applications actually. So here what is the advantage of gallium nitride hemp based devices compared to counterpart of silicon based biosensor or biomarker actually, that the gallium hemp biosensor actually one can find in the not only healthcare systems actually, one can find in the environmental monitoring and industrial also actually. Okay. So, so this is the details of that argon gallium nitride hemp transistor. That the properties of argon hemp transistor actually compared to silicon based devices actually, it has high mobility, high concentration, and it is chemically stable actually. Okay. So the uh, and also it is non-toxicity actually. So this is the main advantage of hemp based devices for biosensing applications actually. Because I am not going to discuss other parameters actually, because that biosensor actually one can find uh, made on different other materials actually. Here I have listed only comparison between the silicon and gallium nitrate actually. Okay, so that that hemp is actually, it is nothing actually MOSFET actually. It is equivalent to MOSFET actually. It is normally on devices actually. One can operate in the depletion mode actually. Okay. So if you look closely here, so compared to silicon actually, that gallium nitrate based devices, it has high breakdown voltage, it has high thermal conductivity, and it has more electron mobility compared to silicon material actually. That's why actually, so that hemp based transistor, if you will choose argon or gallium nitrate based material, which will give better result actually. So this is the schematic diagram of hemp structure actually based on GAN structure actually. So as I already told actually, this is the nothing actually. It is equivalent to mass structure actually. Here that mass actually, that the current will, that our current transposition, it will take at the surface actually here, whereas in hemp actually, that the current transport mechanism from source to drain actually, it will take through two-dimensional electron gas actually. So hemp is actually, if you'll look that hemp structure actually, is nothing actually heterojunction between the algane and the GAN actually. Okay, so that because a hemp structure actually made on wide band gap materials, that algane, aluminum, gallium nitrate is the wide band material actually. If we'll algane, gallium and gallium nitrate material, that is a heterojunction actually. So in that heterojunction actually, at the interface actually, due to that wide band gap materials and that gallium nitrate is, it has piezoelectric properties. Due to that piezoelectric properties and that wide band gap material actually, there is two-dimensional electron gas is present at the interface, which is here this particular device's current transport is taking place at the interface. So due to that two-dimensional electron gas present in the this hemp transistor actually, from that speed, particularly if we'll use that hemp transistor for any applications actually, you will get better speed actually. Okay, so mostly this hemp devices actually, they will you can find for different applications, including that common application of hemp transistor is actually high power devices or high frequency applications actually. This hemp devices one can use not only for high power and high frequency application, one can use for biosensing applications. As I already told actually, this devices is as good biocompatible actually. So that is the reasons actually. Okay. So here we already know actually. So before going to fabricate any devices actually, first actually we have to model the devices to optimizing the devices topology or structure actually. So in this work actually, so we have actually used actually Silmaco software for to simulate the proposed hemp structure. And first we have optimized actually, then after optimizing the hemp transistor by using this particular simulation tool, then we fabricated that optimized devices, and we have subsequently tested for biosensing applications. Particularly actually, we have tested TH and heavy metal ion present in the water actually. Okay, so that because as I already told actually, that high resolution of pH measurement actually become but most importantly not only biomedical industry, other chemical industry also actually, because that deviation in the pH level in the our blood actually, it will indicate the metabolism state of human bodies actually. So that is the reason actually. So we have tested that our fabricated devices for pH sensing applications actually. Okay, so for the design hemmed structure by using Silvaco software actually. So this is the proposed structure actually. This is the hemmed structure actually. In this hemmed structure actually, one can optimize the device's performance by using or by introducing post performance layer in the structure actually. Okay. So by introducing post performance layer in the proposed structure actually, we can improve the total performance of the devices actually. Okay. So in this hemmed structure actually, how one can use as a biosensor actually. Okay. So for example, actually, this is the hemmed structure actually. In this hemmed structure actually, that gate region actually, one can deposit actually functionalization layer, which it will react with the biomolecule samples actually. That functionalization layer actually, it may be for example actually to detect that pH samples actually, or pH level present in the blood or saliva or serum actually. So here we have that one can choose Al23 or SiO2, which will react with the pH sample, because pH sample is actually, in pH sample actually, there is acidic and base actually. That acidic and base actually, it will react with the hydroxide group of either SiO2 or Al23 layer, and it will generate or it will change the surface potential of the this hemmed transistor, which will affect the output characteristics, particularly drain current across this devices actually. So this is the working principle of hemmed structure for pH sensing application actually. Similarly, actually, one can deposit that if a different functional material or layer for different diseases actually. Okay. So whatever diseases you wish to detect or study actually, we have to select appropriate functionalization layer actually. So to choose that functionalization layer is more important actually, because why I am telling actually, that is some functionalization layer actually. For example, actually, this Al23 layer actually, one can use, for example, actually, to detect a particular heavy metal ion detection actually. But that Al23 actually, it will detect actually not only, for example, mercury, or and also it will detect actually lead ions also. So you have to choose appropriate functionalization materials actually. So that is the more important actually. So in this simulation actually, um, in this first actually, as I already told actually, to optimize the hemmed structure actually, one should introduce boosting layer actually. So what are the that boosting layer actually? So here, if you'll look this structure actually, this is the simple hemmed structure actually, which is consisting of argon, gallium nitride, and gallium nitride heterostructure. This is the high electron mobility transistor one can use for high power application or high frequency and biosensing applications actually. So here, when you will grow, or when that hemmed structure on the substrate actually, or when you will form heterosenson alkane with gain material actually, there may be scattering actually. So how one can avoid that scattering actually, if we introduce space layer between the alkane and the gallium nitrate actually, we can avoid scattering actually, because that alkane gallium nitrate is the ternary material actually, which will, if you use this alkane aluminum gallium nitrate material for high electron mobility transistor application actually, due to that ternary material and that is scattering actually, it is depending upon that mole fraction of aluminum concentration with gallium nitrate actually. Okay. So in this simulation actually, so we have chosen actually 0.3 aluminum molar ratio, because we have that the aluminum molar ratio is more important actually, which will decide the scattering across this devices actually. So we have introduced aluminum nitrate spacer layer between the aluminum gallium nitrate and gallium nitrate structure, and then we have used actually aluminum nitrate as a nucleation layer between the substrate and gallium nitrate actually, because whenever you will grow any semiconductor materials on selected substrate, one should take care of and one should take care of misalignment actually. Okay. So whenever you will deposit different material on the substrate actually, that is because normally they will use epidaxial layer actually. Okay. So if if you have to choose appropriate material which will not create any stress strain across this interface actually. Okay. So that's why actually by using aluminum nitrate nucleation layer actually, you can avoid stress strain across gallium nitrate and the substrate actually. Okay. So that purpose one can choose aluminum nitrate as a nucleation layer between the gallium nitrate and the substrate actually. Okay, to avoid the stress strain. Okay. And also we have used that gallium nitrate cap layer, which will reduce the traps at the surface actually. Okay. So there may be possibility of different traps may be present in the aluminum gallium nitrate surface. So if you introduce gallium nitrate cap layer above the aluminum gallium nitrate, that will reduce the different type of traps present in the surface aluminum gallium nitrate surface actually. Okay. So these are the first performance layer one can introduce in the traditional hemmed structure, and we can improve the total performance of the devices actually. Okay. So while simulation actually, you can study what is the effect on this performance booster layer actually. So we have simulated this proposed structure in the Silvaco, that these are the proposed structure details actually, including that what is the thickness of individual layer, and we have used the Silvaco software and we have simulated, and after simulating that proposed structure in Silvaco software, then we have studied the output characteristics of that proposed devices actually, particularly we have measured output current. So in this graph shows actually what is the effect on the space layer and nucleation layer with and without the nucleation and phase layer. What is the effect on the output current? Actually, one can easily observe. So without that nucleation and the space layer, actually, that compared to that with and without nucleation layer, actually, that current is actually it is increased actually. So after including that nucleation and the phase layer, actually, we can easily observe actually that the output characteristics that the drain current is actually drastically increased actually. So whenever you are going to use this hemp transistor as a biosensor actually, to calculate that sensitivity actually, one can use this drain current as a measurable that is sensitivity measurement purpose, or you can use that trans conductance value for to measure or to calculate the sensitivity actually, because trans conductance also more important parameter of this devices actually. And also we have tested or we have measured actually that breakdown voltage and frequencies analysis also, because as I already told actually this hemp structure you can use other application including high power devices, high power and high frequency applications. So from this output that characters output result or output characteristics of this proposed devices actually, one can easily understand actually of
Hello, Perry sir, are you there? Your voice is not audible. Perry sir, are you there?
yes, I am there. My voice is not that.
Yes, sir. From last 2 minutes, whatever you said that it is not audible and your presentation is also not visible, sir.
No, now I am audible.
Yes, you are audible, but sir, your presentation is not visible. Yes, sir. Now it is visible, sir.
Okay, thank you.
Okay, sir.
So we have used the different passivation layer to study the effect on the output characteristics of this proposed structure actually, including particularly that drain current actually. So from this result actually, one can easily observe actually after introducing that passivation layer on the that proposed structure, drain current is drastically increased actually, and that optimized that passivation layer thickness is actually 2 to 5 nanometer actually. Okay, this is the optimized details parameters actually. So here and in this model actually we have used actually charge detection method actually. So after optimizing the devices parameter actually, so we have model actually for to test the particular applications actually. As I already told actually that the developed structure, that hemp structure actually we wish to we wish to test for pH or other heavy metal ion detection actually. To test pH and other heavy metal ion detection actually, we have model that model is actually charge uh, charge based model actually. Okay, So that charge based model actually, it is nothing actually, because each protein may have different charges actually. So for example, actually, if you wish to use this proposed devices for biosensing application, particularly if you wish to detect cancer, particularly breast cancer actually, in that breast cancer sample actually, there is a protein that is called actually CRP2 actually. So that that concentration of CRP2 for healthily and diseased person actually, that range may be different actually. For example, actually, here one can easily see actually that CRP2 protein concentration for healthy and diseased person actually, that clinical relevant concentration of that CRP2 protein present in the either saliva or serum or blood sample is actually minimum is 4, maximum is 6 for healthy person actually. If person is affected by that either breast cancer actually, then that CRP2 concentration that or that value actually for that diseases person actually, minimum is 19, maximum is 13 actually. This is the clinical relevant concentration actually. So by using this parameter actually, one can easily call corresponding charts by using this relation actually. This relation is actually that charts relation for how to calculate that charts, different charts for different proteins actually. So that charge actually, it is nothing actually, concentration of that particular protein into avocado number actually. Okay. So to get that concentration of different proteins actually, one should refer corresponding that protein concentration actually. Okay. So by using this simple relation actually, one can calculate the charge concentration for different proteins or tissues or saliva or serum. Then that corresponding concentration actually we can apply across the interface of the proposed devices. Then if you measure the output characteristics of this proposed devices actually, one can find actually there is effect on the output characteristics actually, particularly that the drain current actually, there will be variations actually. So for example, actually, after calculating different that charts for particularly here CRP2 that proteins for healthy and diseases person actually, that corresponding charge actually we have introduced at the surface of the high electron mobility transistor. Then we have measured the output characteristics actually. So from this model actually, easily one can observe that there is more variation in the output characteristics actually. So from this characteristics actually, easily we can calculate the that del I. Then that by using that del I actually, one can decide the sensitivity of the that devices actually. Okay. So sensitivity, either one can use that del I or one can use that trans conductance parameters actually, because in HEMT actually, why we have chosen that drain current and the trans conductance parameter for to calculate the sensitivity actually, because this drain current and the trans conductance actually we have observed actually more variation while if you are exposing the biomolecule samples on the surface, which will altering the surface potential of the hemp structures actually. So due to that change in the surface potential actually, current transport across the two-dimensional electron gas, actually, it will change actually. So that is the working principle as I already told actually. Okay. So whereas actually that counterpart is silicon-based biosensor actually, they will choose actually threshold variation for to calculate the sensitivity for that silicon-based biomarker actually. Okay. Hemp-based structure actually, if you are going to use that hemp structure as a biosensor, then that optimized or recommended parameter for to calculating the sensitivity is better. We have to choose drain and transconductance. If you are designing biosensor based on the, for example, FinFET or a simple MOSFET based silicon MOSFET based biosensor, then you will find more variation in the threshold compared to output characteristics actually. That's why actually, so then in case of silicon based biosensor, they will prefer threshold old variation to calculate the sensitivity output, that is sensitivity of the biomarker or biosensor. For hemp actually, from our simulation as well as that experimental result, we have observed actually that there is more changes in the drain and transconductance parameters. Okay. So here we have varied the concentration of that CRP proteins, and we have measured the corresponding output characteristics. So from this characteristics, actually, one can easily understand whenever you will increase the concentration corresponding drain current of that proposed that biosensor devices also, it is increasing. So this is the observation actually. Okay. So, and also actually we have tested this, we have, we have optimized actually not only that performance boosting layer, and also we have vary the uh, gate length, and we have also studied the what is the effect on the output characteristics of the proposed devices actually. Because so one can optimize the devices, particularly this hemp and MOSFET actually, one can introduce different boosting layer, other way of improving the performance of this proposed devices is actually one can tailor the tailoring the gate length. So in this study also, we have varied the gate length and we have studied the output characteristics of this proposed devices actually. For example, actually, here we have varied the gate length from 0.5 micron to up to 16 micron. Here we have shown actually 2 micron, 3 micron and 5 micron. You will we can easily observe actually that output characteristics of this hemp structure is actually, it is depending upon the gate length also actually. So whenever you will increase the gate length, that output current also, it is changing. Okay. So that also we have optimized actually. So because whenever you are designing either hemp or silicon based devices for biosensing application actually, that researchers actually mostly they will prefer more sensing area actually, because if you use that nano sensor actually, it will give good sensitivity and selectivity actually, but that sometime actually if you're not chosen appropriate sensing area actually, it will lead false output actually. Okay, so that is the reason actually, particularly for the sensor actually, we should prefer more sensing or more functionalization layer area actually. Okay. So from this simulation result actually, so we have tested actually that a hemp transistor is suitable for biosensing application or not actually. So from that characterization or from that output result actually, so it is observed that actually that proposed structure actually one can use for biosensing applications actually. So we have optimized actually that the devices in terms of mole, that aluminum molar ration, it should be in the 0.2 to 0.3. If you increase more than 0.3, then you will observe more scattering across that devices actually. If you will increase, for example, 0.5 and 0.6 actually, more scattering will be there actually. Okay. So that is one observation. And also that passivation actually, so also role actually one should use passivation layer, either silicon nitride or aluminum nitride, which is that thickness of that passivation layer, it should be less than the 2 nanometer actually. Okay. So here, after optimizing the hemp structure by using simulation study actually, then we went for fabrication actually. So here, this is the fabrication flow. Here, first actually, this is the proposed structure actually. In this structure actually, so that hemp structure actually, we have grown on silicon substrate by using molecular beam epitaxy technique. Then next steps actually, we have formed ohmic and source drain contact. Then we have deposited actually passivation layer, and we have then we have introduced actually gate contact, and after gate metal or gate contact actually. So finally, actually, in that source drain pad opening, actually, this is the sequence of fabrication steps which is we have followed for this proposed structure actually. Okay, so this is the details actually. So first actually we have open or we have deposit ohmic contact actually. So that ohmic contact actually we have chosen actually for example to grow sorry, so this is the full details of fabrication details for this proposed structure actually. So as I already told actually we have grown gallium nitrate on the selected substrate by using FDXL technique actually. So metal organic chemical vapor deposition is the best method for to grow epitaxial layer on the selected substrate actually. Here we have chosen silicon substrate. One can choose silicon or sapphire substrate actually. Compared to silicon, sapphire is the best substrate, because if you choose in place of silicon, if you choose a sapphire substrate actually, you will get better AB layer actually. Okay. So there is no stress strain across the substrate and that ground layer actually, because that is the best method actually. MOCVD is the best method actually. And we have first, and then for source training patterning actually, we have used actually optical lithography technique actually. And we have that to deposit source and drain actually, we have optical lithography technique, and we have used actually UV wavelength 360 nanometer actually, because since it is optical lithography actually, we have used that 360 nanometer lithography technique actually. Okay, lithography technique, and to deposit that source and drain metal actually, because to create that source drain patterning window, we have used optical lithography. To deposit that source and drain metal actually, we have used actually EV evaporation method, and that source drain contact metal thickness is actually in this work actually we have deposited that thickness of 210 nanometer. That source drain, that stack, that metal stack is actually consist of Ti aluminum, nickel, and gold actually. So this combination of this stack is actually we have used for source and drain actually in this proposed structure actually, and we have used actually mesa isolation, patterning, and mesa etching also we have used actually for to deposit passivation layer, and here that passivation layer actually we have chosen silicon nitrate, and that deposition method is likely plasma enhanced chemical vapor deposition, and that passivation layer actually thickness of that passivation layer is actually 100 nanometer, and that mesa etching that depth actually we have etched actually around 200 nanometer actually 200 nanometer, and here we have created that gate recess hardening to introduce that functionalization layer actually. So for that purpose actually we have used again that same optical lithography pattern where that so for source and the drain whatever that optical lithography pattern we have used actually same technique we have used for gate recess patterning also. Then for gate deposition actually we have used atomic layer deposition, and that gate metal is actually here we have used actually that gold actually that thickness of that gate, sorry, we have used that aluminum atomic layer deposition for gate oxide actually, because here in this work actually we have deposited or we have fabricated two type of devices actually. One is a planar structure, another one is circular structure actually. Okay, so we have studied actually two different topology, structure topology. One is linear, another one is circular pattern actually. So for gate oxide deposition, we have used the aluminum ALD technique actually, atomic layer deposition. So that gate deposition and the padding actually we have used actually E-beam evaporation actually, because we know actually that electron beam evaporation method is the suitable method for to deposit metal. MOCVD is to suitable method for to deposit epitaxial layer. E-beam is the suitable method for to deposit any kind of metal for contact. Okay, then we have used to opening that source and the drain padding also we have used the optical lithography technique, and that source and the drain padding also we have used actually reactive ion etching method actually. So we have used more than 6 masks for to get this proposed structure actually. Okay, so because for example, this is the details of mask details actually. Okay, so mask details actually we have used more than 6 masks for to develop this proposed structure actually. So this is the full details of that fabricated structure actually. What is the individual layer thickness actually? Here that is stack, sorry, that total empty stack details is presented actually. Here silicon substrate is actually 400 micrometer, that micrometer. Aluminum nitrate is actually 160 nanometer, and aluminum gallium nitrate we have deposited multi-layer to avoid the scattering between the to avoid the stress strain between the substrate and that nucleation layer. Then that thickness of gallium nitrate is 1.05 micrometer, and that nucleation layer and that another space layer also we have deposited actually. That space layer is 1 nanometer, aluminum nitrate is 1 nanometer, and gallium nitrate is actually 2 nanometer. That aluminum gallium nitrate is 22 nanometer actually. Okay, so this is the individual layer thickness of this proposed structure actually. Here I have shown actually particular um, uh, gate length actually, because we have we have fabricated actually more than 50 devices, varying the gate length and varying the other parameters also. Here I have shown only one example actually how we have varied the that post performance layer thickness and that gate length actually. Okay. So here it is the mask details actually. Okay, so mask for to opening the source and the drain, and gate add source and that ohmic source and the drain gate and passivation layer actually. So this is the details of mask actually. So after depositing individual layers actually, so we have tested or we have studied the corresponding electrical and surface properties of that fabricated structure actually. So this is the details of lithography systems actually. Okay. So here this is the more details about actually what is the sequence of that fabricated steps we have followed for to opening source and the drain. And so while depositing source and drain actually, so what are the other steps we have followed actually? For example, actually to open that source and the drain actually, we have used the photolithography technique, and we have used the positive photoresistive material actually. That photoresistive material is actually PDMA, that polymer materials actually. So we have used the positive photoresistive material for to opening the source and the drain. Then we have used actually lift off method for to remove the photoresistive materials. And finally, we have etched that photoresistive material by using appropriate etching solution. Then after depositing that source and the drain by using appropriate that lithography and the E-beam technique actually, we have post annulled that deposited metal source and drain metal contact to avoid the surface defect actually. That post annulling we have taken at the 850 degree for 30 seconds in the N2 ambient actually. One can choose either N2 or organ actually. So this is the ohmic contact after fabricating that ohmic contact on the stack surface actually. Then we have measured corresponding thickness by using thickness measurement setup actually, and we have verified actually what is the that is stack layer actually. Okay, not only that, all both ohmic and Sarki actually. So we have measured actually what is the deposited metal contact thickness, not only source and drain. So after depositing that gate also, we have ensure that deposited thickness of source and drain and gate also. Okay. Okay. So this is the details of how that while depositing source and the drain actually. So what are the metal we have used actually? How much time we have taken for to deposit that metal layer by using E-beam technique. So how much current it is taken for that respect to metal also here they have listed actually. So then, as I already told, actually we have used the Mesa etching for to etch the that able layer for to deposit passivation layer actually. Okay. So we have used actually that silicon nitride passivation layer, and that the thickness of that passivation layer is 100 nanometer. As I told, actually we have used that plasma enhanced actually low power chemical vapor deposition, and also we have used that plasma enhanced CVD technique for to deposit that passivation layer actually. So this is the details of gate patterning. So after passivation, actually, we have deposited gate layer. So after depositing that same process we have followed, like whatever the process we have followed for source and drain, same lithography and etching and lift off process we have used for gate patterning method also. Okay. So after depositing that gate, actually, we have studied the different electrical and surface characteristics. These are the equipment we have used for depositing and the characterization of that fabricated structure. So thermal evaporation, XRD, SEM, AFM, TEM, we have used for both electrical and surface characteristics study. Okay. So this is the photograph image of fabricated structure. So as I already told, actually, we have fabricated that minimum size is 2 micron, maximum size is actually 18 micron gate length. Actually, we have fabricated, and this all devices actually subsequently we have tested for uh, electrical and optical and biosensing applications actually. Okay. So in this study actually, as I already told, actually we have developed actually two type of devices. One is planar, another one is circular pattern actually. So this is the top view of same image of that circular hemmed structure actually. So that advantage of circular pattern compared to planar structure actually, here you can avoid actually to mask actually. Okay, to mask actually you can directly avoid also, and compared to planar structure actually, this circular pattern hemmed structure actually, it will give better devices performance and it will give better sensitivity compared to planar devices cycling. Okay. So that is the advantage of circular pattern hemmed devices cycling. Okay. So after fabricating that devices cycling, first we have tested the output current of that fabricated structure actually. Then this is the first is the drain current characteristics of fabricated structure with the different gate to source voltage. So from this output characteristics actually one can conclude that a fabricated structure is actually it is performing it is giving better result in terms of drain current. So by varying the gate to source voltage, and also we have measured that output characteristics for different gate length, and also we have studied the that conductance. Okay. So this is the experimental setup we have used for to test the pH range present in the sample actually. So we have preferred actually different, we have chosen actually different pH solution actually to test the that fabricated structure is suitable for to sense the pH range. So we have chosen pH ranges 9.2, 7 and 4, which is this range is covering both acidic and base. So we have exposed this selected pH range on the fabricated structure, and we have measured corresponding output characteristics. So if you look actually, so for example, actually, so here that there is more variation on the output characteristics actually. Okay, more output variation on the output characteristics. So from this result actually, it is evident that actually that a fabricated structure is suitable for pH sensor actually. So this because I already told actually that value or range of that pH range is actually more important actually. That pH range is actually it is indicator of many bases actually. Okay. So this is the conclusion of that hemp based devices for biosensing application, particularly pH. Actually, we are not tested other biomolecule samples actually. So it is under process actually. So as of now, actually, we have tested that fabricated structure for only pH sensing applications, and also we have tested this fabricated structure for heavy metal ion detection cycling. This is the again what is the effect on the width also? Okay, gate width also we have varied actually, not only gate length, width also we have varied actually, and we have studied the output characteristics. So this is the fabrication stress that flow for a circular pattern. Okay. So that conclusion is actually we have calculated that is sensing matrix actually. So that planar structure sensitivity is actually, so in terms of current actually 1.52, that is circular pattern sensitivity train current is actually 1.74, and also one can conclude actually that a fabricated structure is suitable for pH detection actually. Okay, so that same this fabricated hemp structure, as I already told also, we have tested for not only that pH, we have tested that phosphate solution to confirm or to ensure this fabricated structure is suitable for pH or any other solution actually. Okay. So this is the packed devices actually. So here we have again measured both pH as well as other potassium, that phosphorus buffer solutions. Particularly we have tested pH as well as NaCl3. So compared to pH actually, if you use this fabricated structure for to detect NaCl3, this fabricated structure is not giving better sensitivity actually. Okay. So similar way actually, this proposed that hemp structure actually, we have simulated for heavy metal ion detection actually. So this is the structure actually we have used for to detect heavy metal ions present in the water actually. Okay. So we are not used that whatever structure we have proposed for pH actually here we have used a different structure for heavy metal ion detection cycling. Okay. So we have fabricated that same hemp structure for heavy metal ion detections here. Instead of silicon, actually, here we have used actually a silicon carbide as a substrate. Okay. So by using almost that same fabrication technology, actually, we have used for to fabricate this proposed structure, and we have tested for heavy metals. Okay. So I'm not going to repeat this all the steps actually. So these are the fabrication steps actually we have used for to develop this hemp. Okay. So after fabricating actually, so that fabricated structure actually we have transfer into the TCP board, and we have packed the devices. So here, for example, this is the packed uh, the devices for heavy metal ion detection cycling. So here this we have taken wire bonding for to test different heavy metal ion detection cycling. Okay. So here this is the drain, source, and gate bed actually. So through this pad actually, one can easily expose samples through this pad, and you can measure corresponding output characteristics of this devices actually. Okay. So here we have tested for mercury ions. So that fabricated structure is cycling. It is detecting mercury ions actually. To detect that mercury ions actually, this proposed structure actually, we found used actually that APTC functionalization layer actually. So one can use to detect heavy metal ions like mercury or lead or any other metal actually. One can use lead or SiO2, but this study actually we have used actually that APTC functionalization materials actually. Yeah. So, however, actually, we have developed and demonstrated that hemp structure for pH and heavy metal ion detection actually, but still there is a scope for to study the stability, because so we have observed actually, so there is gate leakage, and that fabricated structure, while subsequently we have tested for reliability actually. So we have observed actually that the output characteristics of that fabricated structure is actually, it is degraded actually. So that is the reason actually. So there is still scope for us to study further to improve the performance of these proposed devices actually. It is under process. So this is the summary. Okay. So as I already told actually that the limitation of the device is actually long-term stability, and the miniaturization issue of the hemp sensor still remain unsolved actually. Okay. So cost also compared to silicon-based biosensor uh, to develop that hemp-based biosensor actually it's required more cost actually. It is the limitation of this hemp sensor actually. Advantage is actually chemically is stable, but the cost is high. So any query regarding this hemp actually? If you have any query actually is asked actually. So next time going to discuss actually another topic actually, that is MEMS actually. So what is the MEMS? So MEMS is actually micro electromechanical systems actually, which is contain both the electrical, mechanical, even optical block. Okay. So by using this MEMS systems actually, so one can use for different applications actually, because that the working principle of MEMS system is actually either uh, um, optical or piezoresistive, electrostatic or magnetic or piezo electric also. Okay. So this is the example actually how one can find MEMS system or sensor for different domains actually. So one can find this MEMS sensor for including biomedical applications actually. For example, one can find pressure sensor, microfluid applications, and so on. Okay. And also you can find this MEMS sensor and actuator in the traditional application like oscillatometer, including and that you can say that to find this MEMS sensor and actuator in the um, even printer, like inkjet printer. Actually, we are using pressure sensor. Actually. Okay. And also you can find this MEMS sensor in the RF, including mobile applications. In mobile applications, actually, we are using different sensor, including touch screen, actually. And also you can find this MEMS sensor and actuator in the optical domain also. Okay. So that MEMS devices actually for particularly that health sector actually, one can find actually, um, for example, here glucose or blood pressure sensor. This all actually you can develop by using MEMS technology also. Okay. So this is the example actually how one can use micro mechanical electromechanical system for to develop different micro needle one can use for healthcare systems. Actually. Okay. So in MEMS actually, particularly actually to develop biosensor actually, one can choose either silicon or polymer or compounded materials actually. So because each material has its own advantage and disadvantage actually. So as I already told actually that working principle of MEMS sensor and activator is actually piezoresistive, electrostatic, piezoelectric and then magnetic actually. So in this particular study actually, we have used actually piezoelectric working principle actually. Okay. So discuss this one actually. So here our work is actually mainly focusing on MEMS sensor for energy harvesting applications actually. So in this work actually, we have developed actually micro needle actually one can use for either energy harvesting application or biosensing applications actually. So here we have used for piezoelectric nano generator applications actually. So what is the need for piezoelectric nano generator actually? Because we know actually, so recent past actually advancement of nano technology and nano materials actually, n number of nano devices have been successfully developed and demonstrated because of their advantage actually, including small size, fast response, simple fabrication, low power consumption, and that advantage of nanomaterials, including compared to bulk material, it has high surface to volume ratio, easy to fabricate. Okay, so even though there is nano devices actually, after developing this nano devices actually, if you wish to use that fabricated nano devices for a different application, including pacemaker or biomedical applications actually, we have to cover those devices actually. So traditionally actually we are using traditional power supply for to power those nano devices actually. Indirectly it is occupying more space, and it is required uh, recharging the that battery actually. Okay, that is the constraint of nano devices actually. Okay, or nano biosensor actually. So therefore, development of nanoscale copper devices for converting mechanical source to electrical source is more important and necessary actually. So to overcome these challenges actually, so researchers are finding alternative way to power those nano sensor and actuator in the healthcare systems actually, because if we have developed a nano sensor or nano MEMS sensor, after implementing or that devices in our health human body, it is very difficult to remove, and it is remove and replace it actually. So that's why actually, so our research is focusing on that to develop nano devices which should develop self power as well. Okay. So these are the energy harvesting systems actually, type of energy harvesting system types actually. So energy harvesting actually, one can to harvest the energy, one can use the solar, thermal, RF, and other principle actually. Here we have chosen to energy harvest actually, we have chosen that piezoelectric working principle compared to other traditional techniques is because that advantage of this working principle is actually, as I already told actually, either you have to recharge or replace the battery which is placed in the biomarker actually. So that is the reason actually we have we wish to develop self-powering the devices actually. Okay. So here that self-powering nano devices actually, which will convert mechanical energy into electrical energy by using piezoelectric properties actually. To fabricate that piezoelectric nano generator or biosensor or bioactuator actually, so we have to choose appropriate materials actually, or appropriate devices actually, because piezoelectric devices actually, it is which will convert electrical to mechanical or mechanical to electrical energy, so both the sensor and the actuator actually. Okay, so these are the few piezoelectric material I have listed actually. So among this piezoelectric material actually, in this work actually, we have chosen zinc oxide material for to develop zinc oxide based MEMS sensor for energy harvesting applications actually. So it has advantage compared to PGT actually. PGT is first of all bulk materials, and zinc oxide actually you can easily form or prepare in the form of nano structure actually. And compared to PGT actually, this zinc oxide has high piezoelectric coefficient which will reset the output characteristics of that devices actually. Piezoelectric coefficient is the most important parameter which will decide the output characteristics of this MEMS devices actually. Okay. So we have prepared that zinc oxide thin film by using simple thermal evaporation technique. This is the flow chart of we have followed for that grown zinc oxide nanostructure actually. So after preparing that zinc oxide thin film, first we have studied the structural characteristics, including XRD. So from this characteristics that a prepared zinc oxide thin film is a single crystalline. This is the corresponding same image of that prepared nanostructures. From this same image, one can easily conclude that a fabricated zinc oxide thin film is in the form of nano needles. So this nano needles actually one can use for different applications. Actually. Okay. So here, for example, actually how one can use this nanostructure for energy application, that energy harvesting applications actually. So that zinc oxide is basically actually piezoelectric materials. So that piezoelectric material which will convert mechanical energy into electrical energy with the combination of piezoelectric and semiconducting properties actually. Okay. So this is the schematic diagram of that how one can use that zinc oxide nanostructure for energy harvesting applications. So before using energy harvesting applications, actually, how one can ensure that fabricated structure, that nanostructure, piezoelectric zinc oxide thin film nanostructure is capable for to converting mechanical energy into electrical energy. So here we have chosen atomic force microscopy technique to demonstrate that the fabricated piezoelectric material has that capable of converting mechanical to electrical energy. So here, so we have considered or we have chosen AFM technique or AFM setup to apply mechanical force on the fabricated nanostructure. So we know actually in the AFM system or AFM experimental setup, there is a AFM tip which is made on silicon nitride. Through that tip, by using scanning mechanism, one can apply force on the surface of the fabricated nanostructure. Okay. So here, please you note down actually here we are not applying any bias across this nano structure. Here we have considered single nano needle zinc oxide for to demonstrate the energy harvesting application cycling. Okay, so here we have considered single nano needle. How this single nano needle it will convert mechanical to electrical energy. So through this nano tip actually, if through scanning left and right actually, episode actually, so we know actually while scanning through AFM tip actually, so if that tip is moving from, for example, left to right actually, if whenever that tip is deforming the nano structure actually, that the structured side actually, it will generate positive potential. Compressed side actually, it will generate negative potential actually. Since here this nano zinc oxide nano structure material is the n-type material and which is connected with the ground that AFM tip is connected in series with ammeter and resistive load and connected with the ground potential actually. So while if that tip is while touching that structured side, that zinc oxide nanostructure is getting structured side is positive potential, compressor side is negative potential. So here that AFM tip is basically here we have considered that platinum tip and that platinum tip metal and this semiconductor material is actually, it is nothing actually Schottky diode. Okay. So this Schottky diode actually now it is getting actually reverse bias when that tip is touching in the structured side because that n-type zinc oxide is getting negative, that tip metal side is getting positive. So whatever charge generated across this single zinc oxide nanostructure, actually it will be accumulate. It will not transfer to the load while structured processing actually. So while moving that when moving that AFM tip from structured side into the compressed side, then that compressed side actually compressed side actually then that AFM compressed side N-type zinc oxide is getting negative, and that P-type actually metal is connected to the ground potential compared to that zinc oxide negative, that AFM tip is connected higher potential. So there's a simple this circuit diode between the AFM tip and the zinc oxide single nano diode, single nano that wire, that diode, it is getting now forward bias actually. So due to this forward bias, whatever the charge developed across this single nano rod actually, it will transfer into the load actually. So this mechanism only actually we have adapted to study the piezoelectric properties of that fabricated zinc oxide nanostructure. This is the image of 3D output and image of both that zinc oxide surface and the silicon surface. We have subsequently that is tested by using atomic force microscopy. So we have chosen 5 into 5 micron scanning area. One is that the first one output is for zinc oxide nano needle surface structure. Another one is actually for silicon nano wire. Okay, so from this output 3D image characteristics, actually one can easily observe actually that the first image contain or consist of n number of voltage pulses actually. Okay, so it means actually each nano needle actually it is generated voltage pulses actually. That's why actually we have observed that n number of voltage or pulses actually it is observed in the output or that surface while scanning actually. Whereas actually that same AFM technique actually, that scanning method actually we have performed on the surface of the silicon material actually, but that silicon material actually it is not generated or it is produced actually voltage pulses for individual silicon nanowire actually. So from this characteristics or from this output result, one can easily ensure or understand actually. So only here that the zinc oxide nano wire is actually it is capable to generate mechanical energy into the electrical energy in the form of voltage pulses. Here there is that voltage pulses is our absent in the silicon surface, because silicon is the no silicon is a it is not piezoelectric. It is that silicon material is not it is has not piezoelectric properties actually. Silicon is not a piezoelectric material. Zinc oxide is the piezoelectric material. So silicon nanowire, it will not generate or it will not convert mechanical energy into electrical energy. So by doing this experimental verification, actually, we have ensured that a fabricated zinc oxide nanostructure is suitable for converting energy into the mechanical energy to the electrical energy. Okay, so this is the we have demonstrated here. This same nano rod actually you can use for biosensing application actually. How one can use this nano rod for biosensing application actually. So say that suppose this fabricated nano sensor, if you use as a functional layer which will react with the any biomolecules actually. So after reacting with that biomolecules actually, that mass of individual nano rod actually it will increase. So due to that mechanical mass actually, if there is deflections, because you can develop this single nano zinc oxide nano rod actually. Here I have shown actually only surface actually. You by using micro electromechanical systems actually, you can develop actually that zinc oxide nano rod in the form of cantilever structure actually. Okay, so for example actually here, so this is the example actually how one can develop cantilever structure by using micro electromechanical systems actually. So in this cantilever actually, if above this cantilever actually, if you deposit zinc oxide nanostructure, which will act as a functionalization layer for to react with the biomolecule samples, then this simple cantilever actually you can use as a MEMS biosensor applications actually, because after reacting with the biomolecules, as I already told actually, that the mass of this cantilever actually, it will vary due to changes in the mass. There will be deflex in the group mass. If you will measure that deflection by using either concept of measuring the change in the resistance or change in the deflection, or if your structure is in the form of electrostatic, one can measure either capacitance or the resistance. So by measuring that change in the resistance and the capacitance, actually, you can measure the respective quantity of that biomolecule concentration for biomolecule applications. If you are, or if you are using this MEMS sensor for pressure sensor, then by measuring that displacement, actually, you can measure corresponding pressure. Okay, so this is the application of MEMS sensor and actuator for different applications actually. Due to that time limitation actually, I have not discussed actually what is the basic principle of not basic principle actually, how one can design and develop piezo resistive, for example piezo resistive or piezoelectric sensor and actuator actually. For example, actually, we know actually, suppose if somebody want to develop a piezo-resistive sensor actually, so that piezo-resistive sensor actually, after developing that simple cantilever structure actually, so if we are able to measure stress strain across that cantilever due to that biomolecule reaction actually, then by using that technique actually, so we can measure that biomolecule applications actually. Okay. So here, this is the old relation actually, how that piezoresistive sensor actually, how one can use actually either metal or semiconductor material for the piezoresistive applications actually. Okay, compared to metal actually, semiconductor material they will prefer for to design a piezoresistive sensor in MEMS applications actually, because compared to metal actually, that a semiconductor material has high G factor, and that H factor actually, which will decide the change of resistance in the MEMS sensor actually. Okay, so silicon is the best material for piezo-resistive sensor actually. Okay, zinc oxide is the suitable material for piezoelectric MEMS sensor actually, because there is a difference. So silicon is the best material for piezo-resistive sensor. Zinc oxide is the best material for piezoelectric sensor actually, because silicon actually it is good material for change in the resistance, even small amount of change in the mass actually, or acceleration or pressure actually. Okay, so by using that concept, so silicon actually you can constrain, for example, piezoresistive sensor in the form of diaphragm structure. In this diaphragm structure, if you will apply pressure on this diaphragm structure, this structure actually it will work as a pressure sensor actually. Okay, So here, for example, this is the capacitive RF MEMS chips actually. So this also same diaphragm structure actually, but that application is different actually. Here, this structure actually, it has capacitive structure actually. Here, that the top one is gold, bottom one is that is silicon dioxide actually, and here they will use actually another metal actually. So in between the two metal actually, if you will deposit silicon nitrate or simple air gap actually, which will act as a dielectric medium, and that dielectric medium between the two electrodes actually, that is, it is nothing capacitive structure you can use for RF MEMS application to transfer high frequency signal from one end to another signal actually. Okay. So this is the example actually. So because this is the actuator, not sensor. So by applying appropriate bias signal on this capacitive structure, you can deflect this structure by deflecting that structure on the, for example, this structure actually, this is, it is nothing actually coplanar waveguide transmission line. So if whenever that beam, it will deflect on the ground actually, so we are able to transfer RF signal from one point to another point actually. So here, this is the how one can develop uh, cantilever structure by using bulk micro machining technique actually. Okay, so that main difference of CMOS and MEMS fabrication technique is actually, see in MEMS actually, by using etching process actually, they will develop actually record structure, whereas CMOS process actually depositing multi-layer actually, they will achieve record structure actually. This is the main difference actually. Okay. So mostly here silicon they will use as a MEMS substrate and the functionalizing layer material for to create different structure actually. Okay. Okay. So that's all from my side actually. So this type of devices as I already told actually. So we can use as a cell power devices in health care applications actually, because this zinc oxide, since it is a piezoelectric material, you can use as a biosensor as well as self-powering devices. You can use this kind of devices for to measure heartbeat. So to measure that heartbeat actually, or to measure blood flow in our human body, through that blood flow, it will get mechanical energy and it will convert into the electrical energy. That converted electrical self-powered that generated electrical energy, we can use as that is to power those devices. By doing this way, one can avoid replacing and recharging the bio nano devices on the healthcare system cycle. Okay. So thank you. So once again, I thanks Professor Amit Joshi for giving me this great opportunity. So if you have any doubt actually, so please feel free to send the mail, or you can refer our research recent published articles.
9 a.m.
Okay.
10 a.m. to 10 p.m. Okay.
Sir, any queries?
Yes, sir. Means if any queries, you can post it over here if you want to ask right now. Otherwise, definitely, as sir suggested, that you can mail sir. Mail ID is already with you. Okay, because I have shared all expert email ID along with the schedule only. So you can ask sir individually also. And if you have any specific question that you want to ask right now, we would be happy to take it over here.
Sir, if they are Sir, if they are writing any query in the text box or chat box, actually, please let me
Yes,
know.
sir,
Actually,
we will let you know, but currently
I
we haven't
am
find out anything.
I'm keen to answer for those queries, sir.
Yeah. Yes, sir. Yes, sir. But currently there is no query right now. Okay. So it
Okay,
seems
okay.
that there is no query right now. If they have, then maybe they can contact you individually.
Sure,
Okay.
sure, sure.
Okay.
Thank you, sir. Thank you so
sir,
much.
for joining. Thank you, sir, for joining with us. Thank you. So with
Okay,
this,
thank you, sir.
yes, yes, yes. So
Thank
with
you.
this,
So
we
with
are
your,
taking 5 minute break. Okay. Our next expert is about to join. So we will start at 12:07 sharp. Okay.
okay, thank you so much, sir. Okay.